한 1분 정도만 기다렸다 시작할게요. 잘 들리나요? Yes라고 해줄래요? 혹시 들리면? 예, 시작하겠습니다. Okay, so welcome back. And so we continue our discussions about the programming language that supports some unusual features from the perspective of study on programming languages, or very common features from the perspective of practical programming languages, like input, output, and then failures, and so on. So here's a quick reminder about where we are. We are discussing about such a programming language with failure, input, output. One of the reasons we study about this language is because this language is quite powerful. And so the mathematical tool that we need to analyze this language is a lot more sophisticated. And that's key. I mean, in fact, these tools are, in a sense, provides a way. Well, it's a bit like some like initial. It will prepare you to study some more sophisticated techniques that's needed to study functional languages. So we try to look at the semantics of this language. And as I said before, the key part of the semantics is to specify the type of interpretation. So in particular, the type of interpretation for command. And I said this type has to be changed because of these extra features in this language. Okay, sorry, let me. Okay, it has to be changed because of these extra features. And then the changed domain looks like this. For every command, its interpretation is a map that takes states and returns something called omega. Okay. I said informally elements in omega is like a computation trees, but we want to study its formal definition. And then because we want to make things more rigorous so that we can analyze this programming language mathematically. And this omega, we said, is something that satisfies this isomorphism. So it's a pre-domain, which means that it will have it will come with order. And then this pre-domain will satisfy this isomorphism, which looks like this, sigma head. So omega. and lift it. And where sigma head is equal to. So I'm going to specify what I can explain to you what this isomorphism means exactly. But last time, before talking about what this isomorphism means exactly, I told you about what this plus operator and multiplication operator means. This is a sum construction for predomains. This is a product construction for predomains. And then intuitively, this isomorphism say every element in omega, it can be understood as an element of something on the right-hand side. And what's happening on the right-hand side tell us there are 5 kinds of outcomes. One is, this is a normal terminations. So program terminates normally. So we have a outcome of the normally terminating program. And then we have another sigma, which is a part which we use to describe abnormal termination by failure. And then this the middle part, this is about outputs. And then the last part is about the input. I mean, last among this sum is input. And then this bottom, which is usually here, is for non-termination. So really, this isomorphism say, I mean, in the computation, the immediate response that we can get in the computation there are 5 kinds of immediate response. Program terminates normally, program terminates abnormally by failure, or it outputs, or it inputs, or it goes into infinite loop without saying anything, without like producing any output and so on. And then you can see that omega appears on the left-hand side, on the right-hand side here. And omega appearing on the right-hand side intuitively say, if my program terminates, produce an output, then it may continue and do something else. So that's why we have an omega on the right-hand side. The same way, if we take an input, that's the next, in a sense, step, visible step of the computation. And after the input, it will do something. It may be output, input, and so on. Okay. And then to understand this isomorphism more formally, we studied about the construction for predomains. So we studied the 2 constructions. One is for sum, the other is for some products. And the definition of, if we have a say if I have a predomain P0 and then P1, I mean, I talk about applying sum for not just the 2 predomains, but arbitrary number, but it's enough to understand what's going on in the sum case, of binary case. So the P0 plus P1, it's a new predomain. Its underlying set, underlying elements is of this form. So some index I together with X, where index I is either 0 or 1. And that index really tells us where this element is coming from. So X is from PI. Okay. So it's really disjoint union. And then the order is defined for each component separately. And for products, it is a pair. So it's a usual Cartesian product that you are used to. And then, so it's a set of pairs obtained from each of the component P0 and P1. And then the order is defined component-wise. And then I told you for each of these domains, it's a bit like a type constructor in programming languages. And these pre-domain constructor come with constructor and destructor. And then, so I talk about 2 ways of, constructor for each of these cases and destructor for each of these cases. The constructor for P, this sum, was injections, which is, I wrote it I0, which is a mapping from P0 P0 plus P1. We also have a constructor 1 that takes element P1 to P0 plus P1. Because P0 plus P1 is a disjoint union, I mean, this embedding is just embed elements in P0 into appropriate copies by putting in the tag 0. I1 behave the same way. It's the kind of embedding that you are expecting. And for the products, the destructor is something that's simple. So which is a projections. So the projection is defined like this. And that has the usual meaning. It takes the first component pi 0, pi 1, it takes the second component. And then I said there are, we have a way to construct elements in the, destruct the elements from the sum is given by, what John called source toppling. And in my case, it's some operator that's written like this. So, but I think the better way is to tell you the context. Well, somehow it doesn't respond. So if we have mapping, say, from some predomain P, suppose we have a predomain P and some predomain Q. If we have a mapping F0 and F1, that goes from, I think maybe drawing a picture is better. So if we have P0, P1, here's a P, Q. If we have a continuous function F0 and F1, continuous function for G0 and G1. And I said there is a way to construct an element of this products of P0 and P1 by using F0 and F1. That's what John called target toppling. So if I wrote it like this, that's going to be a map from P to P0 plus P1. And it's defined as you expect. Is take element in P and then apply F0 and F1 to each component. And then also, therefore, the destructor part, we have G0. Somehow. So we have a G0, G1. That takes an element in the sum. And then produce an element in target. So this destructor in sorry about this. Somehow I see. Okay. So it's G0 and G1. If it's an ith component, we just apply the ith component, Gi of x. And this corresponds to the case analysis, like a case statement in OCaml and Haskell. And then usually programming language provide this constructor not in the form that I wrote here, but more direct form. These are the two constructions. And then I also talk about this operator F0, prime, F1 prime, and F0 prime plus, F1 prime plus, where F0 is a prime is from P0 to prime, P1 to P1 prime. And this guy is a mapping from P0 cross P1 to P0 prime cross P1 prime. And the same way for the plus. So this I call these functorial actions. So these are the things that we have. And in fact, this functorial actions that I wrote at the bottom is available for most of the pre-domain construction that we will consider in this lecture. Okay. Now, what should we do? So once we have all of these, now we can define what this isomorphism means exactly. Okay. So beforehand, I informally talk about this isomorphism, but I can now talk about this isomorphism. So we're gonna look at this domain more closely. Definition of omega. So what does omega? How omega is defined? Here's a formal definition. It's not actually a definition. It's one important property of omega. So omega is some predomain. So it's a predomain. And it's such that it satisfies the following property. So omega, and we think about this sigma hat plus integer times omega plus to omega. And then so this is sigma hat, as I said, is a sum of two copies of omega, the sigma. And then this is z is a set of integers, but we said set of integers can be understood as a predomain. So we have applied this cross product construction that we just talked about on this z and omega. And then here is all the continuous functions from the predomain z to omega, but z is just set. It's a discretely ordered predomain. This is just a set of all the functions from z to omega. Okay, and that is again a predomain. We combine them by using this sum operator for the predomains, and then finally we apply this lifting operator at the end. So the right-hand side is a predomain that's obtained by applying various predomain constructions. And the left-hand side is just omega itself. And then we say there is two continuous functions. One is called phi and psi. The other is called phi. They are continuous functions. And then these continuous functions has to satisfy the following property. The property is that if we combine them together, compose them together, so first apply the psi and coming back with phi, that's going to be an identity function on omega. And if we do the opposite way, first apply phi and then psi, that's going to be an identity function on this complicated stuff, so sigma hat plus top and bottom. Okay, so this is the definition of isomorphism. We have two continuous functions, phi and psi, and these continuous functions satisfy this property. Okay. So, but what does that mean intuitively is that every element in omega actually can be understood as one of the cases. So it can be either belong to this sigma hat, and in particular, it may belong to the first copy of sigma in sigma hat, or second copy of sigma in sigma hat, and so on. So every element in omega is one of this 1, 2, 3, 4, 5 cases. So that roughly means every element in omega is either represents normal termination, abnormal terminations, and or the output and input were non-termination. So, but there is another important property which we are not going to, go that much in details. But so the other important property we are not talking about is that that's what we're actually going to talk about a little bit. It's called minimality. So just like the initial algebra stuff that we talk about when we define the abstract syntax, this omega, it turns out it's something very much related to the initial algebra. So, and in particular, it's if we set things up properly, it can be understood as continuous initial algebra. Okay. I didn't tell you what it is. I will tell you what it is a little bit. But for us, the one important consequence of this is that we can do the definition in a syntax-directed way. It's not exactly syntax-directed, but we can do some definition in a style very similar to the syntax. Sorry about this. Somehow this Microsoft Note became very sensitive. Some change happened. The syntax-directed definition. So why we need this? If we want to use omega to define the semantics, we need some way to define a function on omega. So you will see where we need this. And then this syntax-directed definitions, or something similar to the syntax-direct definition, it is going to be a very crucial tool that we can use to do something on omega. Okay. So, right. So this is the predomain is satisfy this property. And so I will tell you a little bit more about this minimality, what this minimality actually means. This minimality means that, and also that's really the formal definition of this continuous initial algebra. This minimality means the following. If we happen to have some predomain P, so if we happen to have a predomain P, and then we have a continuous functions, V, maybe V prime, that goes from sigma hat Z times P plus P bottom. So if you have a continuous function that goes from the right-hand side to the left-hand side, this P doesn't have to be the same as omega that we are defining right now, okay? It's just some P which satisfies this property. If we have something like this, then the following thing happens. So the for P together with this P prime, which is a continuous function, there exists a unique function, continuous function. Let's call it just F, that goes from omega to P, such that the following diagram commutes. So we have I will wrote first the diagram and explain to you what it means. So we have, if we go back to omega, okay, we have something like V for the omega as well. V prime, which is exactly this V. that play a similar role as phi prime. So we can think about this following two setup. One is we have sigma hat plus times omega bottom to omega. So we have a phi here. And then for p part, we also have something similar. Cross p and p omega goes to p. And here we have a phi prime. And then what this now is this statement, which is characterization of this minimality, say there is a map that goes from omega to p. So which is map phi prime. And then there's such step part to say actually this phi prime satisfies this property. So we can lift phi prime to a map from this complicated stuff on the left-hand side to the complicated stuff on the right-hand side using the functorial actions, this functoriality that I told you before. So here, in this what functoriality tells us is that we can apply this like a sum construction, product construction, not just on the pre-domain, but also continuous functions. So in this case, we have an identity on sigma hat. That's for this part here. And then we add them by plus. We have an identity on set of integers. That's for this part. Now for part that goes from omega to p, we apply phi prime. No, this is not actually phi prime. So here we have f. So here we also have an f. And then I'm going to tell you what it is, but here we can do something similar for a set of integers. I mean, this functions that goes from integers to p, we can also define a map using f that goes from the functions z to omega to functions z to p. Okay, and then we finally apply this lifting operator that's also can work on the continuous functions. Okay. So what this statement to say is that this diagram commute, which means I'll tell you what these two guys are soon, but then assuming that they are defined, what this diagram tells us is that the phi followed by f is the same thing as, so this direction gives the same function as going the other direction. Okay, and then more intuitively, what this tells us is what phi prime does on each of the cases and what phi does in each of the cases, they are in a sense compatible via this function f. And although I'm not going to go very much in details, I mean, what people call what I explained to you as an algebra and algebra homomorphisms, if you by chance looked at my lecture notes, there I explained something very similar there. And then this definition of algebra homomorphism exactly corresponds to the commutativity of this diagram. Anyhow, so then what these two guys are, I mean, this is Z F. I mean, that bottom. This is a map from continuous functions to omega to continuous functions to P, and GF take a function G, and what it does is that it first apply the function G and then it compose with F. If you apply function g, that maps integer to omega. And then if I apply the function f, that maps element from omega to element in P. So that's what this one is doing. And this lifting, okay, lifting is any domain is from P. I mean, we're not using P. So if you just say Q bottom to R bottom. So where if your K is a continuous map from Q to R, so then this K lifted is a mapping from Q bottom to R bottom, and this behavior is exactly what you expect. If we plug in bottom, it returns bottom. Otherwise, it returns just K of X when X is just an right. So when X is just an element of Q. So omega that we are using here, it's something very special. It satisfies this isomorphism. It has a psi and b, which is this isomorphism. And then it also satisfies the minimality property that I explained to you below. And if you don't understand what minimality that I just told you, it's all completely okay. What it tells us is that we can do something, define something in a way that's very similar to the syntax-directed definition. If you remember the syntax-directed definition, there was a definition by case analysis. So we can do something like a case analysis-based definition. Okay, so now how to use this omega. So to use this omega, we will do some, and also tell you about the benefit of this minimality and also syntax-directed definition. I will give you, had to define a few operators here. Let's call it 1. Okay, so the operator I'm defining is is this. So we will define something called iTerm, which is a mapping from sigma to omega, and we'll define something called I abort. That's also mapping from sigma to omega, and two more, I out. That's mapping that takes z cross omega to omega, and I in. That's it takes function and to omega. And the last bit is I bottom. It takes a singleton set bottom and then map it to omega. Okay. So I will give you the first definition and I will ask you to fill in the rest. So then this first definitions. So here's a reminder about omega. This board is not so big. Sorry, it's somehow. Okay, this omega, if you give a quick recap about what omega is. So we have, this was psi and p. Then there was sigma hat. plus omega functions, and then bottom, and where sigma hat was sigma plus sigma. Okay. So we want to define this type of map. They are, in a sense, maps that allows us to embed all of the 5 cases into this domain omega. How we define this I term? So I term take state sigma, and then we have to map it to construct an element in omega. So to do so, we first embed sigma to sigma hat. So to do so, I mean, to embedding sigma to sigma hat is putting some index, right? Index is 0, because it's constructed as a sum type, and we want to put the sigma to the first copy of the sum type. So we put the index is 0 and put a sigma. And then now we have another there's some case where sigma head appears in the first component of this sum construction. So we put another index 0 to indicate we are now talking about embedding the element into the first part of this sum. And finally, we have to map this element in this sum space into omega using phi. So we apply phi here. Okay. So, and then for I in, here's how I do it. I in, we take a function g, which is an element that maps integer g to omega. And then we embed it to the third component of this sum construction. So that we embed it to 2 and g. And then we map it to the element in omega. So we map it by phi. So now it's an exercise for you. I mean, there are 3 more cases. I mean, these 3 cases, fill in these 3 cases. I will give you 2 minutes to do so. So Robert, the reason we added this 2 and 0 is because the definition of this sum space is defined by disjoint union. And to make sure we have a disjoint union, we put every element in sigma hat with index 0. So here's a reminder of sum. We have a p, sum of p plus q. This is not equal to p union q. Okay, because P and Q might have the same element. So instead what we do is that we put every element in P with a tag 0. And then we put every element in Q with a tag 1, and then you take the union them together. So that's why if you put an index, this index is 0 here, that's used because we want to map sigma, which is an element in capital sigma, into this space sigma hat. And sigma hat is defined by this the sum of 2 copies of sigma. So that's and then we have to put 0 to indicate we want to embed an element to the first component. So if you want to put map, okay, good. Okay, so here's a solution. It's quite simple. For abort, it's very similar to the I abort and state. It's very similar to what we did before, except for the case of I term, except that instead of mapping it to the first component of sigma hat, we map it to the second component sigma hat, because that's the component reserved for the abnormal termination. So we are mapping it to here. And then for this output, if we take integers n and then element omega, and then we map it to, it's the second component of the sum over there. So we put 1 and omega. And then we use phi to convert this to an element in omega. And bottom is something very similar. So for bottom has only bottom elements. But for the bottom elements, we already have a bottom element here. So what we have to do is just map it to using phi there. So that's how we solve this exercise. The reason this is quite important is because this is the one that allows us to the syntax, this case analysis based or syntax direct definitions. We have a term, aborts, and then outs, in, and I over there. And the minimality, if you really want to understand why this is okay, you can go back to the minimality and solve some exercise that I put in the lecture note. And these 5 give us to define something recursively define something by case analysis and induction or recursion. Okay. So what does this mean? So I will write a word syntax directed definition. So what does this mean? This means that suppose we want to define some function f, okay, that goes from omega to maybe some space p. So what should we do? Okay. And it's actually not very easy because omega is not defined explicit. It's not like set of integers. It's defined in the, I didn't really give you explicit construction of omega. I just said omega satisfies a few properties. It satisfies minimality and also satisfies some isomorphism condition. And actually, there is, some space that satisfies these 2 conditions, these are unique. So up to isomorphism. So this is, in a sense, completely characterize this space omega. But anyhow, we want to define some function f from omega to p. Okay, why I want to do it? Imagine we want to define the semantics of sequential composition. Okay, so then denotational semantics, we have a C1, which is a mapping from sigma to omega. And then we have C2, which is a mapping from sigma to omega. Okay. And then now, so from this C2, we want to, in a sense, for sequential composition, what we want to do is we want to define meaning of sequential composition, like, this composition operator. But this is not good because it doesn't type check. This is C2. The meaning of C2 takes element in states, but meaning of C1 will produce an element in omega. Okay, so we can't really compose them together. So what we have to do is somehow use C2. Okay, we use this guy, and somehow we want to define something called C2 star, which is going to be a mapping from omega to omega. Once we do so, we can compose C1 and C2 by just usual function composition because it type check. Okay, so then the question becomes, how can we do this, right? More rigorously mathematically. And then I'm telling you what these 5 cases I defined to you. And then if we use recursions, we can do it. This methodology is, I'm not going to tell you why this methodology allows you to define some function without any ambiguity at all, but which is actually coming from the minimality that I told you. But this is a methodology we can use to define this function, something like the C2 star. Okay. So what is the methodology? The methodology tells us the following. It says that, okay, let's get rid of this. Says that to define function f, we only need to we can define function f by case analysis. And then when we do the case analysis, then what are the cases? These cases are the 5 cases that are coming from the top. So each of these 5 cases that's written on the top, I term, I abort, and so on, they are talking about some element in omega that can be constructed, right? So by using I term operator, we can construct an element in omega. By using I abort, we can construct an element in omega, and so on. They talk about 5 different ways of constructing elements in omega. And then by case analysis, I mean that to define function f, what I need to do is to say how function f should behave for all these 5 cases. And the minimality ensures this is enough. Okay. But then while defining function f for these 5 cases, sometimes we can't give an immediate definition because cases like I out, it contains the omega as one of the components, right? We need to, in a sense, give a definition here. We need to use either, you can call it induction or you can call it recursion. Okay. So we need to do recursion or induction to handle the case where omega appears in the case already. Okay. So if the syntax direct definition say, if you just use this case analysis, and then whenever it's needed, you can use recursions, then that gives a legitimate definition. So I think the best way to understand this is actually looking at this operator. So let's assume that we are given G, which is a mapping from sigma to omega. And then what we want to do, G star, that goes from omega to. So what's important here is now that domains, which used to be sigma, is now changed to the omega. Okay, so that's what's the important part. So, and then we follow this methodology, which is that the methodology tells us do case analysis, and if it's necessary, we can define things by recursion or induction. And by in doing so, we can define this G star. And here is the definition of G star. And because there are 5 cases, we consider 5 different inputs. The first input is I term of sigma. That's the first case of the 5. In this case, I mean, this is sigma is an input state, so we just apply G. So that's one definition. I mean, this is a definition for the terminating case. And aborting case, then we have an option. And then the options, we can apply G to sigma. That give us one way of defining G star, but we're gonna define it as a map which doesn't do anything. Why is that? Because we want to define G star so that G is applied only when the element in omega is a normally terminating computation. For all the rest, we don't do, I mean, so if it doesn't terminate normally, we don't want to apply G. And then the third case is an out. And then in this case, we define things in terms of induction. So we say we put out here, and then we inductively apply G star on omega. And then for the elements in function G, actually, maybe not using G. Okay, here. So in takes a function that goes from Z to omega. So we define it as it's still I in. And then for the elements, we take an input, which is a natural integer Z, and then we apply this input to K. That's going to be an element in omega. So an element in omega. And then we recursively or inductively apply G star to Kn. Okay. Now finally, we have a G star I bottom. And then for this case, we don't do anything. We just apply I bottom here. Okay. So this is I mean, you can see that the definition here that I gave you is by the case analysis. And then while giving the definition, I use inductions, okay, like this. Okay. And then when I apply, I mean, inductively or recursively call G star, I always applied it to some subcomponents like omega and something that's coming from K, the subcomponent. And if you do so, this gives always legitimate definition. Okay. And as I said, the formal justification about why this is okay can be done by using this minimality condition here. So then let's understand what this is doing. Then I will give you an exercise. So what's going on here? Okay, I said the elements in omega can be understood as a tree. So let's think about some typical elements, which say if we take an input and then we produce an output, and we return a state term with some state sigma. Okay, so that's the one element in omega. So if you apply this G star, what should happen? So intuitively what should happen is that our intention is to apply G, which is the transformation of final states, only to this last guy. Okay. Now, if you view what's written on the left-hand side here as an algorithm, and then if I apply this algorithm to what the expression that's written here, then this output is going to be this. For input case, it doesn't change because that's what this definition is telling us. Output case, it doesn't change, and it just recursively apply the G. So that's what's written here. And we hit the base case, which is the termination case, and then we apply G there. So it's going to be written by G sigma. This. Okay. So in terms of trees, we can view this as a I in. There are -1, 0, and 1, 2, and so on. Then each case we have a out. Out is 1. And then there are terminating with some state sigma. So that's our input that's given to G star. For this input, what it does is that you look at the leaf of the tree and you apply to G there. So the tree looks exactly the same, except that for the output part, that the leaf, if the leaf is the termination, the normal termination, you replace it by another tree produced by G. But if it happens that for some of the case, the output, that's not exactly the same as what I wrote over there. Output is abort, and then the leaf is abort, sigma prime. And this part remains, it doesn't change. I out, I abort, sigma prime. So that's the intent, what's formalized by the definition in this second case in the definition. So what's written there is really telling us we want to apply G. We look at the computation tree, and we want to apply G only at the leaf, which you talk about normally terminating computation. Okay, which is normal termination. There we want to apply G only for those cases. Now here's an exercise I want you to do. The exercise is defined. So this erasure disappears. So here's an exercise. So suppose we have a function h. Okay, what this function does is that it takes state sigma and return state. And then what we want to lift this h using dagger notation such that it's going to be a map from omega to omega. But what we want is unlike this G star, which does something only for the normally terminating sigma, we want to apply h to normal termination as well as abnormal termination. So for instance, if you apply h dagger to, let's write it, this computation tree, I in 0, 1, so on. And then let's say input is 0, we terminate with sigma. Input up, the input is 1, we abort with sigma prime. So input is 0 or non-positive. We always terminate with sigma. If input is positive, we always abort with sigma prime. So suppose we are given element omega looks like this. then we want that H dagger returns a computation, the element omega that represents the computation where the returned state is changed regardless of the state is coming from normal termination or abnormal termination. So here now I term, but instead of returning sigma, we have a h of sigma. For the one, we have I abort. Instead of sigma prime, we have h of sigma prime. Okay, so define given h. So define h prime in a, say this using the methodology that I told you. Yeah, that behave like the one that I just explained here. So I'll give you 2 minutes to do so. Okay, so here's the definitions, and definition is quite simple. So if you have I abort, start with abort, then we said this is still I abort, then we apply H there. And a stagger, it's a termination, it's still normal termination, but we apply H to sigma. And if it's an output, sigma and omega, and then we say it's still output, but we recursively apply H dagger to omega. It's an input. If it's an input, we have then still an input, but we just recursively apply H dagger to the output in what follows after the input. And then for bottom, we don't do anything. So that's the definition. And you can see that the definition is very much like a program. We do 5 case analysis, and then we are allowed to do the inductions, well, recursion. And also this is very similar to the syntax-directed definition that we see. And this similarity all comes from the fact that they are all about, they are all related by this abstract mathematical sense, which is, they are all initial algebra in some setting. Okay, so we now know enough to define the semantics of the language. Okay, so here's a reminder. The semantics of interpretation function is going to take commands and return a map from sigma to omega. Now, using all the things that we talk about, here we can define this. So for the base case, we have for assignments, it takes state sigma, and then you have to return something in omega. So what we do is that, but assignment always terminates. So we produce some state and embed it using this I term. So what state we're going to produce is what you expect. We update the value of x using the value of expression e, and abort and fail. And this is a failure, so it's not difficult. We use the abort case, and then we return some input state sigma. Now, what should we do the sequential composition? So to do the sequential composition, we first run C1 sigma. And then that's going to be its output is live will in omega. Now to run C2, we want to run C2 only for the normally terminating case. Okay, C1 may go on to the infinite loop, may abort. We don't want to run C2 on those cases. We want to run C2 only those cases when C1 terminates normally. And that's exactly captured by lifting change the C2 using this star. Okay. So we run C2 using the star that we defined above. So C2 star that we defined here. Okay. Right. So, and then for if then else, C1 else C2. And the definition is also simple. We just do the usual if then else case, it stays sigma, if it's true, then we just run C1. Otherwise, we run C2. And while is a bit challenging, but the pattern is the same as the one that you see before. So we define some fixed point of some operator f, then we run sigma. And then this fixed point is defined like this. F is a map that takes some omega to sigma to omega. And then what it does is that it takes this f and the sigma, and if the Boolean conditions is true, so then you run the body of the loop, and then it runs f lifted. Okay, big F represents the rest of the loop, so if we run f lifted, otherwise we just return sigma, but to run the normal terminations, we have to put it into iterm. Now we have about 6 minutes, okay? So here are two things I want you to do. So the one is we want to define this question mark. Want to take an input for the variable x. Actually, there are three. Output of some expression. And finally, new variable declaration. So define these three cases. I will give you 2 minutes, and then I will answer it afterwards. Okay, so for for the input, what we do is that we take an input. So we use this in to create some element in omega that represent the input case. Then we have to provide a function that takes an integer and then return some element in omega. So we take an integer n, and then now the element in omega that we have to produce is sigma, where x is updated by the input value. So we return I term, and the state is sigma, where x gets updated with the input value. And for the output, we create an element in the output, and then the output that we are producing is value of this expression on the sigma. And then the omega that we have to produce is the state sigma itself. So here we write it I term and sigma. So what that means is the output doesn't really change the current state of the machine. The last bit requires something that we talk about. So we have to, what we have to do, we have to run C. And then to run C, we run C under the states where value of this variable x is bound to initialize to the expression value of expression e. Okay, and then we run C, but then we have to do something, which is we have to restore the value of the global variable x. So this x is a local variable, and we have to restore the value of the global variable. So how you do it? And then that, and also other important bit is that the restoration of the value of global variable should happen whether in the terminating computation as well as this failed or aborted computation, which means that we have to use these dagger things that we talk about. Now for the dagger things is about state transformation. You take state sigma prime, which is a states, they're produced by C if C terminates or C aborts. And then for state sigma prime, we restore the value of a global variable x to the original value according to sigma. So it's sigma of x. So this is the original value of the global variable x. Okay, so I'm out of time, but here are just some exercise I want you to do. So if you look at the lecture notes, then at the end of the lecture notes, so if you solve the exercises, I think it's of note 5. So if you look at the end of note 5, there are a few exercises. So because I encourage you to do it, because you might ask, okay, what we learned so many things to define the meaning. Okay, what's the point without really doing anything with the mathematical definition that we just came up with? And then this exercise at the end of note 5, they ask you to prove the equivalence, to prove that two programs have the same meaning. And these are the kind of things, that's not the only thing, but there's the kind of things where this semantics can be useful and help you to do something very rigorously. So I encourage you to solve these exercises at the end of the note 5. Okay, so that's it for today, and thank you all for coming. Okay, I hope to see you on Wednesday. So as usual, I'll be around for about 5 minutes. So if you have any questions, you can ask me.